What is up, guys? It's your boy Alonso Rodriguez here, aka McLovin from Superbad. If you guys don't know who that is, back with a brand new video about math to all my fans, especially Mr. Garcia. We're going to be talking about four specific problems, about functions and all that stuff. And the reason I don't have my camera on is because my hair's not too good right now since COVID. Let me share my screen real quick. So just so you guys can know who McLovin is. So if you guys don't know who McLovin is, this is him. This little kid right here. You see I look like him? I don't know why. But I'm gonna stop sharing this screen now and let's get into some action. So all right, let me get a hang of it. All right, my problem's right here. It's y is equal to square root of x plus 3 over x squared. And in this particular problem, we will find the domain, the range, continuity, the monotonicity, symmetry, boundedness, extrema, asymptote, and end behavior. Now, guys, don't get too scared. Mr. Garcia, I know, you never done something like this, even though you're a pre-cal teacher. My skills, I'm going to blow you away with these skills. So, this is a problem. Here's the graph. The first thing you do is you graph it. So you graph it on Desmos, which is the easiest site. And as you can tell, it goes up here and it goes on forever. But we'll talk about that later. It goes up and then it comes right back down. So the first thing you do is graph it on Desmos. Then I'll stop sharing the screen. So the first thing we gotta find is the domain. And the domain is all the x values, right? So on the graph, as you guys saw earlier, on the graph, here it is. The x values are on run horizontal. So now, to find the domain, you equal the equation to 0. So when you equal x plus 3 is equal to 0, you get x is equal to negative 3. But remember, x cannot equal 0 because it's in a fraction. So the first domain is negative 3 up here and 0 in brackets. It's an interval notation. The second domain is 0, infinity, and you get that using this. So then the range is equal y is greater than or equal to 0, since the graph doesn't go below 0 at any point. And it's also equal to because it touches 0. So let's get right into it. So the C stands for the continuity. And continuity is basically when you draw a graph, if you don't have to lift your pen from it, then it's continuous. And if it's not continuous, then it's discontinuous. And in this particular graph over here, let me show you real quick. It's continuous. You don't have to lift your pen to draw it. So that's why it's continuous. Now, it's really easy. Monotonicity. Now this is where the points where in the graph where it increases and decreases. So here there's two. So first it increases from negative infinity, which is over here, to negative 3. And then it also increases from negative 3 and it goes on forever. So we use the asymptote, which is 0, as our second point. So it increases from negative 3 to 0. And then it decreases from 0. I know it shouldn't be decreasing from over here, it should be decreasing from all the way up here, but you have to use 0 as an asymptote. So use 0. So it decreases from 0 all the way to infinity, since it goes on forever down the number line, down the graph. Sorry about that. So let me share my other screen again. So it increases, as I showed you, from negative infinity to negative 3, and then also increases from negative 3, which is where we saw, and it went all the way up to I couldn't find the point, so you use 0, which is the asymptote, and then it decreases from the asymptote in 0 and then to infinity because it goes on forever. So you use interval notation to write them, increasing and decreasing. Now symmetry is basically, it can either be odd, even, or neither. In this case, it's neither because it can't be even. Even is when you can reflect the graph across the y-axis, and you can't do this on this particular one. And then, oh, sorry about that. And then it's not odd. It looks like it's odd, but it's not actually. So it's neither. Now, let me share it again. So there it's neither. And now the B stands for bounded. I mean for bounded or unbounded. And this boundedness specifically. So in this type of graph, it's bounded. The only way it can be unbounded is if it stops. And this right here is bounded. It could either be bounded above or below. So let me share my graph again. It could either be bounded above. So if it's up here, let me show you an example real quick. It could either be bounded right here below, or if it's, or imagine this as the opposite if this was up here. So this right now it's bounded below, and then if this point was up here, it'd be bounded above. But in this case, it's bounded in two places, down here and up there. So it's just bounded. Let me get rid of this so you don't get confused. So now I go back. It's bounded, just bounded. It's not bounded above or below. Now extrema, it's NA. That's the local maximum or minimum point. But in our graph, there's no maximum point. There is, but you can't find it because it goes on forever. So it's just neither. I just put NA. Now, the last two things I want to talk about are the asymptotes and the end behavior. Asymptotes, there's horizontal asymptotes and a vertical asymptote. So let me show you right here real quick. If I was to write x is equal to, let me write it real quick. X is equal to 7. This green line is your asymptote. And these are vertical, of course. But in this case, there isn't any vertical asymptotes since look, the graph keeps on going. So there's no vertical asymptotes, but there is horizontal asymptotes. So if you were to increase it to -10, there's one on this side, but that's it. It doesn't really, it goes on for infinity actually. So it doesn't work. There's only one asymptote right here, which is y is equal to 0. Let me see. And this one's horizontal. So y is equal to 0. You see, the graph does not pass this line. Does not go under it. So that's the only asymptote, which is y is equal to 0. And now end behaviors. End behaviors are basically your asymptotes, basically. So you write LIM, negative infinity, and in the negative infinity, it's 0. As you saw in the previous graph, it didn't go below 0. And then the end behavior on the positive side of the graph, it's also 0. So it's basically your asymptote, but in end behavior. So yeah, guys, that's how you guys do it. That's how you guys do the 7 factors on on a function. That's how you find them.
My name is Aiden Hunter, and today we will be reviewing question 4. The first thing we're going to want to find is the domain, which is all the possible x values that the equation or function can have. Here we can see that it continues on endlessly in the right direction and is cut off by the left, but it is an exponent, so it will continue on forever unto an infinity. That makes the domain all real numbers. The range, to find the range, we follow a very similar pattern, but we look at the y-axis. Here we can see that this continues up into infinity, making that anything above y equals -5, asymptote down here. Monotonicity is when we say reading from left to right whether or not the function is increasing or decreasing over time. Here we see a sharp decrease until it hits roughly -5. Now, for extrema, or the local maximum and minimums the function can hit, we can see a strong minimum seen at y equals -5, or right here, as the function can never pass below this line. Now, there is no maximum, as it will continue on infinitely. And next up, we have symmetry. We can see that the equation is not symmetrical in any way. It is not symmetrical around the origin or on the x or y axis. Now, next on our list is continuity. We can see that this has no discontinuity, as it is one straight line with all values on this line being valid. Now, for boundedness, we can tell that this is bounded below because nothing can go below this point. There's a boundary here. All values must be above y equals -5. This boundary we're going to call a horizontal asymptote and is the only one in this equation.
Okay, so now we will solve problem number 6, which is asking to find 3 functions out of the 12 basic functions, which are these, that have this end behavior. Which means we need to find 3 functions that when x approaches -infinity, the limit of f of x will be -infinity. So in other words, we want to find functions that when the x values of it approach the negative side of the x-axis, the function outputs or y values are negative and have no limit or horizontal asymptote. And we know this because in the book, as you can see here, it shows that for this limit notation, which is the one we were given, it is used to show horizontal asymptotes or limits in the y values of a function. And since our limit here is -infinity, we know we have to look for functions that have no asymptotes and functions where the y values are negative. So now that we know what to look for, we can graph these 12 functions using Desmos or another graphing website and see which 3 functions have the end behavior described here. Okay, so now that we have graphed them, we want to focus on the negative side of the x-axis, where the y values are also negative, which is this portion. So we see that there are 4 functions that appear to be only negative. So we want to isolate those and delete the rest. Now that we have isolated them, we see that one of them, which is this one, f of x equals 1 over x, is the only function that appears to have an asymptote, because as the x values approach the negative side of the x-axis, the y values or the y limit is at the line y equals 0. So we can delete that one. And now we are left with the 3 functions that have the end behavior of -infinity, which are f of x equals x, f of x equals x cubed, and f of x equals int of x, which is the step function. And that's it.
So we have 2 composite functions, f of x equals x squared plus 1 and g of x equals square root x minus 2, and we need to find f of gx. So we're going to input g and f, which will come out as open parentheses square root x minus 2 close parentheses squared plus 1, cancel the square with the square root. You're left with x minus 2 plus 1. Then that will come out as x minus 1.
Hi, my name is Janelle Gonzalez, and I will be doing the second part of what Abigail was working on, which is to find the domain of the resultant function, which is this one. So here's a graph, and we see that it's all real numbers, yet there's no real number that makes the expression undefined. So in interval notation, it would be -infinity to -infinity. And that is demonstrated here in the graph because both numbers go to the negative side as the positive side infinitely.